class about local statistics of super-Brownian motion.
Thank you very much. I'd also like to thank the organizers, of course, for the invitation and really for putting together this splendid workshop. It's been really thrilling to see the amount of research and discussion going on over these last few days. I can't wait to see where it goes from here. The subject of the talk today will be what I'm calling local statistics of super-Brownian motion with a focus on 2 dimensions. And everything I'll say is joint work with Alex Dunlap, who will be joining the workshop next week, but I'm afraid he's not here at the moment. I'll start off with a little bit of an introduction to super-Brownian motion. I think not everyone here is terribly familiar with it. And that introduction will be agnostic to the dimension. And then in the course of the lecture, we'll see why 2 dimensions is a particularly interesting case, and we'll dive into the local statistics. So the general goal when we want to construct super-Brownian motion is to obtain some stochastic object that has a continuous distribution of mass, speaking kind of loosely, and that is undergoing continuous branching as well. And I should add death in addition to branching. And so to do this, we can derive it as a scaling limit of appropriate branching Brownian motions. So the main idea to get continuous mass is to start with a whole bunch of branching Brownian motions independently with a rather high density at the initial condition and allow them to run independently. And we'll of course weight each particle with a relatively small weight so that in the limit we get some continuous distribution. And we want continuous branching. And to get that, it's actually helpful to massively accelerate the branching rate in this process. So what will I do? I'll take some large parameter n, and I'll start a whole bunch of branching Brownian motions from, let's say, just for space stationarity, for simplicity, let me start it from a Poisson point process of density n with respect to Lebesgue measure. So I scatter a very high density of points across space at the beginning, and then I will allow these to run as independent BVMs. And so the parameters of my BVM will be as follows. So I'll want rate 1 diffusion. So there will be no funny spatial scaling going on. But as I mentioned, I want to vastly accelerate the branching and death rate. And so I will allow them to branch in 2 and die at an equal rate, which is proportional to n. So we'll think of the rate as being n gamma, where gamma is sort of like a constant. For the first part of the talk, it will be a constant. So some observations. I have binary branching, and at the same rate, I have death. So this is a critical branching Brownian motion. So the expected population size will remain constant in time, but you have unpleasant behavior like almost sure extinction. And so let me just see what this is going to look like. So I will depict RD as a line here, and I've scattered a fairly high density of points at the beginning at t equals 0. Then I run them, so time is in the vertical axis here, to some future fixed positive time. And I want to see what mass remains at that time. And so this is a critical BVM. So as I mentioned, you expect almost sure extinction. And so by this positive time, we've seen a terrible amount of branching and dying. And so most of these particles will have gone extinct by this fixed positive time. So we'll just see these little vestigial trees that have died out early. Okay. But every now and then, roughly 1 out of every n of our particles will survive to this later time, and it will actually be quite prolific. So it'll have a great deal of offspring of order n. And so I'll represent this more fortunate one in purple. And of course, there's a whole bunch of chaos going on underneath. But the point at the end of the day is when I look and see how many particles I have on the same order at this positive time, I have about n of them. And the exact number will depend on time and gamma and on the randomness in the tree. I've ended up with some reasonable evolution of mass, which moreover gives us a stochastic object in the limit. So the thing I want to emphasize here is if I had taken a slightly slower branching rate that were less than order n, then most of these trees would end up surviving. And you would end up just seeing some sort of average wash that more or less is evenly distributed across the line again. So if I branch at too slow of a rate, I'll just get a deterministic limit of mass. On the other hand, if I accelerate this rate to some higher rate, say n squared, then with high probability, I see no mass remaining at time t, and there's some small probability that I'll have a terrible amount of it. So in some sort of limit, I would get wild distributional fluctuations and I would see nothing, nothing useful. So the insight here is that at these particular rates, a high density of initial particles and a high branching rate, one ends up getting a reasonable limit. So if I denote by xtn the empirical measure at time t of all these particles, then this random measure is converging in law to some object as n goes to infinity. And this object is super-Brownian motion, which I'll denote by SBM. So it's a random measure at any fixed positive time. And it turns out that in high enough dimensions, as we'll see shortly, it does not have a density. So it's a little bit of a singular object to deal with. But nonetheless, we end up with no atoms in the limit, for instance. So we've achieved some sort of goal of a continuum of mass. And we end up seeing a continuum of branching as well that gives us interesting stochastic dynamics as time evolves. And so the last comment I want to make introducing this object is to say that if you squint appropriately, it satisfies a stochastic PDE. So more technically, it satisfies the martingale problem corresponding to the heat equation coming from our unit diffusion plus Feller noise coming from the randomness in our population. And here I'm using dW to denote space-time white noise in Euclidean space. And so I've already tried to motivate it here, but for instance, if we forgot about the stochastic, the spatial dynamics, excuse me, then we would just have a Galton-Watson tree at criticality, which we've run at a very high rate. And then that limit, we would expect to get the Feller diffusion as our corresponding object here. So this is a very natural SPDE, although as I mentioned, in high dimensions, X does not have a density with respect to Lebesgue measure, and so the interpretation of the objects in this equation are a little bit suspect, but I'll forge on. So are there any questions before I start discussing the local statistics of this thing? So I guess that was all intro. I want to look at local stats. So what do I mean by this? Really what I'm interested in is the amount of mass that this random measure places on a small ball. And I'll normalize that with respect to Lebesgue measure. So I would like to understand the behavior of the measure of, say, the ball centered at the origin, space-time stationary, or it's spatially stationary, so the origin isn't particularly important here. I've normalized it by the Lebesgue measure of this ball, and I would like to understand the limit of this thing as r tends to 0. And I've already given some hints that there are likely to be problems in high dimensions. And so I can also write this using a kind of, say, functional inner product notation as the measure x tested against some L1 test function, which is here the volume of the unit ball in Rd times the radius to the d times the characteristic function of our ball. And I'll call this function rho of r for convenience. So it's just the normalized characteristic function of the ball. So I'm testing my random measure against some, okay, admittedly discontinuous thing. And it will come as a surprise to no one in the room that our tool for analyzing this inner product is duality with the Fisher-KPP equation. So BBM is closely tied to Fisher-KPP. And so naturally, we can hope that super-Brownian motion is as well. And I think this provided a lot of the motivation for the development of this theory early on. So let's say U, indexed by time, solves a version of Fisher-KPP. So I've swapped 1 and 0 and such, so that I've ended up with something that is really a nonlinear heat equation. So it's a heat equation with some nonlinear absorption here. So if I have a solution to this PDE, then a calculation using Ito's formula will confirm the following duality relationship, which is that if I look at the Laplace transform of super-Brownian motion tested against some initial condition here, then that is equal to the initial condition of my super-Brownian motion tested against the future evolution of my object U. Yes. There isn't. And that reflects the fact that this measure is continually losing mass under a typical realization, I believe. So I've omitted the expectation here because I've used deterministic initial conditions. I didn't make it terribly explicit, but if you take, I think there's one small mistake here, which is that the empirical measure needs to place weight 1 over n on every particle.
Cole, can I ask a question?
Yes.
So is it hard to see that it converges to a super-Brownian motion?
No, I don't think so. One sort of cheating way to see it is there is a corresponding duality relationship for the empirical measure at time n, or at index n. And those duality relationships will converge as n goes to infinity. So with the appropriate kind of technical uniqueness criteria, that would provide a proof.
Okay. But now you're just working with the limiting object.
Yeah.
Okay.
Yeah. So for essentially the remainder of the talk, I will focus on the limit. Yes.
Okay.
Thank you.
Cool.
So because I chose the initial condition of my empirical measure to be distributed according to a Poisson point process that was proportional to the Lebesgue measure, the initial condition of my super-Brownian motion is just Lebesgue measure. So this inner product is really just the spatial integral of the solution to this PDE. So this is to say that we can essentially entirely characterize this measure provided we have a good understanding of solutions to this PDE. All we have to do is solve it and evaluate its integral. So we're interested in this particular inner product. Our random measure tested against the normalized indicator function of a small ball. So that means U0 is going to be identified with rho r. So I'm trying to solve my nonlinear PDE with initial conditions that are very sharply peaked around a small ball here, and they have unit mass. Okay, so now I have to start lying to you. So this is a unit mass distribution that's roughly at scale r, let's say. So let's just pretend that it's a Gaussian at scale r instead. That makes life easier. So instead, I will treat initial conditions given by g of r squared, where I'm using the notation that g times s, x is given by beloved, let's see, s. Okay, so if I plug it in for a second, I'll see that this Gaussian is indeed distributed at spatial scale r, contrary to the square indicated in the index. And this is the problem I'll actually solve. Again, it turns out if you run through the analysis, they're very similar. The same analysis will ultimately work if I actually use the indicator function of a ball, but for the storytelling, let me work with a Gaussian instead. I want to solve my PDE started from a very sharply peaked Gaussian. Make a comment, when we look at the PDE, well, the first couple terms are just the linear heat equation. So that would tend to evolve the Gaussian as usual, and we would just get g of r squared plus t. But then we have this nonlinear absorption. And this absorption is quite strong when u is very large. So it's quite strong right at that sharp peak where I've started my problem from. So there's some sort of interaction between the free evolution of the problem and this strong nonlinear absorption right at the beginning time layer. If we were to guess that the linear problem dominates, then we would guess that ut is roughly given by the Gaussian at this time. Now it turns out this proxy is off by a little bit. The absorption does play a role, or else there would be very little to tell you about today. But the linear evolution, the heat equation, is always trying to force your data back into looking like a Gaussian profile to leading order. And so it turns out an appropriate nonlinear ansatz is to guess the same thing, but with some sort of multiplicative time-dependent factor out in front that accounts for the absorption. So A will start off from 1 and then will decrease. I'm being very loose with what I mean by this approximation symbol, but for everything relevant here, it's good enough. And the thing I want to point out is that if I integrate both sides in space, well, I've normalized my Gaussian to have total mass 1. And so this multiplicative constant is equal to the mass of ut, which is ultimately what we want. So the real fun is to understand the evolution of this constant under this nonlinear heat equation. And so to get an evolution equation, all I have to do is plug this ansatz into the equation and kind of pray. And so I can do that. So if I plug this in, first of all, whenever the time derivative hits the Gaussian, it will end up canceling with the Laplacian over here. So the free evolution is kind of already naturally taken care of. And all the interesting dynamics for A come from the nonlinearity. And so if I plug this ansatz into the equation and then integrate in space, I will get, so I have to compute the integral of the square of the Gaussian. Now the Gaussian was normalized in L1, not in L2. So it's quite large in L2.
You have
Yes.
A squared missing?
I do have A squared missing. Thank you very much. Yeah. Quite important. So I can run through a quick calculation and I'll find that I end up with a rather large L2 norm for my Gaussian. So it's sort of like a Riccati equation, but it's being driven by some time-dependent prefactor here. And really what we would like to do is take R to 0. So allow me to do that formally at least. If I set R to 0 and I try to solve this ODE by separation of variables, say, then I'll end up trying to integrate this quantity in time. So if I do that, I will have to confront something like this. Okay. And so here we see the transition in dimensions. So if the dimension is 1, then this object is integrable, and you have a nice solution to your equation, which I won't write down. You get some finite answer, which has a correction coming from the nonlinearity, and you'll be able to compute the resulting density of your measure. And so this is one proof that in dimension 1, super-Brownian motion has a density with respect to Lebesgue measure. But once d is 2 or greater, this integral diverges. And ultimately, that's saying that the absorption is super strong. And so if d is greater than or equal to 2, what we end up seeing is this multiplicative factor a of t tends to 0 when we take r to 0. In other words, our process is assigning almost no mass to a typical small ball. Which is what you would expect if the support of the random measure were singular with respect to Lebesgue measure and had measure 0. Okay, so what can I even mean by local statistics? I just get some nonsense 0 random variable in the limit. So the idea at this point is to take advantage of this branching rate, gamma, which I have been pretending is constant this whole time. So let me also focus on the critical case, which is of the greatest interest. So from now on, I'll be working in the plane where this thing diverges logarithmically. And the idea will be to tune down gamma as a function of r so that we get something non-trivial in the limit. So if I actually work with positive r, I compute the analogous integral over here. What will I get? My notes will tell me what I get. Let's see. If I take positive r and compute the analog of this integral, I'll end up with a 1 over 4 pi times log of 1 plus t over r squared times gamma. And if t is positive and fixed, then the whole interior here just looks like r to the minus 2. R is very small. And so this is of order 1 over 4 pi gamma times log of r to the minus 2. So that motivates a choice of gamma that depends on r that cancels out this divergent factor. So for the rest of the talk, I'll now allow this branching rate gamma to depend on r, and I will choose it to be 1 over the log of r to the minus 2. Please excuse me for not pulling the factor of 2 out in front. I think conceptually it's helpful to leave it there. So kind of morally, what am I doing? I've taken my super process and I've said if I want to examine it at a spatial scale, it's very small, and I want to get something useful in the limit, I had better relax the branching and depth a little bit. You don't have to do it too much. You have to reduce it by this logarithmic factor as a function of r. And if you do that, you should be able to get some sort of non-trivial dynamics in the limit. And so what's one way to interpret this ODE that I'm working with, well, I could move everything here. Let's see, there's a couple ways of saying it. I could move everything over here and view this time-dependent factor as some sort of change of coordinates. So this is telling me that there's some other time-like variable that I should work with that would give a more convenient answer. And it just comes from the integral we computed over there. I'm going to let Q denote my new kind of fancy time variable. Now modulated by this reducing factor from the weak branching. This is now a logarithmic time scale. I started with linear time, now Q is defined as a kind of power of t, or excuse me, as a log of t. So if I do this, then I will find that the equation for A simplifies to the Riccati equation. Okay, so it's just a well-chosen change of coordinates. And that's saying that our mass is evolving on logarithmic time according to the solution of the Riccati equation. And now for another fun trip through duality. So the Riccati equation is dual to the Feller diffusion. In the same way that that nonlinear heat equation I wrote for U, which is now gone, is dual to super-Brownian motion. And they're really almost the same fact. This equation is just the PDE, but without all the spatial dynamics going on, up to a different constant factor here. And likewise, with my super-Brownian motion, if I forgot about the spatial dynamics, I should see the Feller diffusion corresponding to my critical branching process. And so if I trace through all the layers of duality, what I'll end up finding is that the expectation of our quantity of interest, which is the normalized mass, that are now slowly branching process places on unit ball, or excuse me, on small balls, is equal to something related to the Feller diffusion, to the Laplace transform of the Feller diffusion, where here Z is solving the Feller diffusion, but now in these funny logarithmic time coordinates. So if you believe all of these algebraic hijinks, we should have a clean relationship between super-Brownian motion and this Feller diffusion. And so in particular, if we work with this slowed down branching, and we solve the SPDE, say, for super-Brownian motion, then for any fixed time and any fixed location in space, in this space stationary setting, the normalized mass that our slowly branching process places on the ball of radius r, centered at some arbitrary point, will converge in distribution as r goes to 0 to the Feller diffusion evaluated at time 1. Why time 1? Well, I've taken fixed positive time up there, so the numerator has exactly the same asymptotic order as the denominator in this log time. And so I end up with this single limiting scalar random variable. Curiously, I get the same random variable for any positive time, doesn't matter. And in fact, if one pushes the analysis further, one should expect that if I test this at different points, I'll end up seeing independent Feller diffusions at those different points.
Can you mention the initial value of your super-Brownian motion?
Would there be a way of, instead of changing gamma, of changing the normalization constant in front of the mass of the ball?
The normalization constant?
Well, no, the normalization function instead of pi square.
Yes. So one way to put it is that, yeah, instead of changing gamma, you could do a process where you, say, put a scale factor in front of x, solve the equation, and then kind of undo that scaling. So there's some sort of invariance to the problem you can take advantage of. And that actually has a useful interpretation. So if you do that and you use the additive property that says that if I start super-Brownian motion from a sum of two things, it'll be equivalent to just independently solving from those two conditions and adding them. What you'll end up getting is a similar result here for standard super-Brownian motion, but averaged a correct number of times empirically. So in other words, if I evaluate this at a standard branching rate, but I take an empirical mean of 1 over gamma copies of that random variable, I will also converge to the Feller diffusion. So that empirical averaging is another way of reducing the fluctuations of this random variable down to unit order. So this is probably a calculation I should do offline. Yeah, I see another question.
Yeah, on the same topic, I might be wrong here, but isn't it known that the super-Brownian motion in 2 dimensions has an exact dimension, like Hausdorff dimension function, which is like r squared log 1 over r log 1 over r or something like that?
Yeah, there's 3
which should imply that. Yeah, I don't know. I mean, in 2 dimensions, it was more logs than just whatever.
Yes.
So then in that case, I think we would have that this convergence holds almost surely with r squared replaced by this extra logarithm factor and so on. And maybe that would partly answer Julio's question also. So if you have a logarithmic correction, then you get this convergence for the normal super-Brownian motion as well, if I'm not wrong, I think, right?
Yes, I think, yeah, so this is something I was discussing with Thomas. So I agree. There is a discrepancy of log between that heuristic and this one. And we suspect that that discrepancy can be resolved through the precise definition of the Hausdorff measure. So the Hausdorff measure doesn't just examine the measure on balls of a fixed size, but of a whole slew of sizes less than this size. And I suspect that kind of the clever averaging over all smaller balls could account for that triple log discrepancy. But up to that factor, you're exactly right. And that Hausdorff measure function exactly corresponds to this result.
If you take only fixed balls and not all smaller ones, then you probably get like the packing dimension or something like that, right?
Yes, I believe so.
Yeah.
Yes. So this should say that the packing dimension is
Yeah.
r squared log whatever r. I think it might take some work to actually prove that rigorously. Yeah. Any more questions before I go on?
So just about the discussion that has just been going on, I think if you look at, so if you don't slow down time, then with high probability you will not have any mass in a small ball, right? So you would have to condition on having mass there.
Yes.
Right, so you would have to do that. And if you do that, then you get like extra log r mass.
Yes.
There, right?
I believe so.
Okay, I find it fascinating that you can kind of relate it to small times.
Yeah. Well, it's not exactly small time because the diffusion is still running at its usual rate.
Oh, I see. Oh, I see.
So there's something a little bit tricky.
Oh, yeah.
But yes, it's the right intuition. So that's more or less everything I have to say about super-Brownian motion. So in what little time remains, I want to provide some kind of external motivation for looking at this problem, coming from some recent developments in the theory of SPDEs, and in particular in the theory of nonlinear stochastic heat equations. One way, I've said this many times now, but I'll say it again. So this is essentially a distinct scaling regime from the typical one considers super-Brownian motion in. So in the typical one, you choose a scaling so that at macroscopic scale, you see interesting fluctuations. And here we're saying if you want to look at a smaller scale, you need to adjust time or the branching rate slightly or take many empirical averages to get there. And so there's been a great deal, and that corresponds also to reducing the strength of the noise. Gamma can always be interpreted as multiplying the white noise in the equation, which I'll write down again momentarily. And so one way to interpret this, let's say fluctuations at scale r, is to say that this random variable I've been studying, so x of t tested against rho, this is actually the same as the spatial convolution of my measure with rho evaluated at the location 0. So I've taken a solution to a rather singular SPDE and I've modified it to scale R, and I've analyzed the resulting distribution. Now you could do another thing. You could mollify the noise from the beginning to scale R and then solve the much more well-behaved SPDE that results. So another option would be to study a version of the SPDE for super-Brownian motion. Now I'll index it by R. But one in which I don't deal with the fully singular noise. So now let me just, let's see, 2 gamma R. So I take white noise and then I mollify it at scale R again. Now it turns out I can't tell you anything about the solution to this equation because there's no clean duality relationship that I'm aware of when we do this. But I would just like to draw a very hazy analogy between the object I'm considering here and this. In some sense, I have taken a singular SPDE and I've smoothed it out at the spatial scale R, but in kind of a different order, let's say. Now I bring this up because this is the more familiar setting for the broader theory of treating singular stochastic PDEs. And so just to bring out explicitly this factor gamma, I could write this as square root of xr over the square root of log of 1 over r. The 2 disappears magically. And so I could interpret this as a poorly behaved SPDE where I have smoothed things out and I've also reduced the strength of the noise by a suitable factor. And so it turns out that this same formal procedure has been getting a lot of attention recently through the analog to the linear stochastic heat equation. So I could draw a formal connection between this equation and something where I put a rather general nonlinearity in the place of Feller noise. So I could consider some sigma of my solution and let me reduce it by the same factor and hit it with mollified noise. Okay, so this is what I mean by a nonlinear stochastic heat equation. And it turned out that in 2 dimensions, this scaling is really the right one to consider. So probably the most interesting case here is when, say, sigma of u is equal to a constant times u. So then we have a linear equation with multiplicative noise. And it turns out in this case, there's a kind of phase transition that occurs. So if beta is less than 2 pi, then there's a result of Caravana, Sun, and Gouras that exactly the same behavior holds. So in particular, working with this linear function, sigma of u, we have the multiplicative stochastic heat equation, and they can show that at a fixed time and a fixed point, this thing is converging in distribution, in their case, to a log normal random variable, which is again independent of the time and independent of the point. And this seems to be the only scaling of the noise that allows us to get something workable in the limit in this particular equation. So we have a formal analogy between this result for the linear stochastic heat equation and super-Brownian motion. And more recent work of my collaborator, Alex, and Yu Gu can show the same sort of result, provided the Lipschitz constant of sigma is less than this critical 2 pi. So I didn't say it when I wrote this result, but it turns out if beta is greater than or equal to root 2 pi, for reasons that are not entirely clear to me, everything blows up. And there's very little known. There are some results at criticality, which is a situation of great interest to theoretical physicists, I gather. And above that, it's a wild world. But Alex and you have managed to generalize this result to situations where you have a general nonlinearity subject to a Lipschitz constraint. So they end up showing, say, the same result to something, which is a solution of a certain forward-backward SDE. So I don't want to write it down. Something involving sigma. But it turns out that, if I ignore this Lipschitz constraint and pretend that their result extends to the square root nonlinearity, then I can plug that nonlinearity into their forward-backward SDE. So if sigma of u is equal to the square root, then the corresponding forward-backward SDE actually simplifies to a forward SDE, which is just the Feller diffusion from earlier. And in fact, one thing I should have said is that the natural time scale for this forward-backward SDE is logarithmic time rather than typical time. And that's agreeing with what we see here. So the kind of broad takeaway is that for the moment, there's this situation where we have some results for the linear equation. Actually, the linear equation is fairly well characterized as things go. Alex and you have generalized these convergence results, these local statistics results, to nonlinearities that have a certain Lipschitz bound. Now I'm collaborating on with Alex on an effort to push the boundary a little bit. So maybe this is hopefully forthcoming. But way over here, we have super-Brownian motion, which is miraculously treatable via the duality. But without that, we currently don't have any method to extend these results to such an irregular case, although all the formal calculations go through as expected. So there's a lot more to be done here, and I'm eager to see where it goes in the coming years. So thank you all for your attention.
We take a few minutes for questions if you have more. Thomas, you have a question? Oh, no? Yes, Vincent.
So you have changed the nonlinearity in front of the noise from the, let's say, the square root to the linear one or so. Is there, let's say, simple explanation that you keep the same scaling in log R in both?
There is. If you do kind of a formal calculation, let's say, you'll find that the major sources of divergences in the generalized equation ultimately come from an integral of a square of a Gaussian in the same way. And so in 2 dimensions, this scaling ends up being appropriate in each case.
Any other question?
Sorry, Chad.
Sorry, Jin Yao, so I missed your question. So please go ahead and ask them. Oh, but I see that Alex has also answered them. But okay.
Thank you, Alex.
I want to ask, can you mention your initial values for your mean theorem? Both for the, can you mention the initial value of Brownian motion?
Well, okay. So the question was, can you mention, well, the first one was switch camera. I think this one has been answered. And that was like 40 minutes ago. And then can you mention the initial values for the super-Brownian motion Feller diffusion in your theorem?
Ah, yes. Yeah, that's important. So yeah, okay, the theorem survives up here. The Feller diffusion should be started from 1. as it is in these cases.
But how about super-Brownian?
And super-Brownian motion here starts out from a Poisson or from Lebesgue, right? Or do you still have these Gaussians involved?
Yes, it starts from Lebesgue. That turns out to not be crucial,
right?
Because we end up examining, the behavior on such a small scale,
right?
So if we start from, say, relatively smooth initial conditions, one would get an adjustment to this result with constants corresponding to actually the solution to the deterministic heat equation at macroscopic scale.
Right.
Because we've basically killed the noise of the macroscopic scale and left ourselves with just the heat equation. And
you had this nice picture in the very beginning where you said one of the trees, and here one they become very, very large, right? And in between there is nothing. So I suspect here, right, your picture would be very local. That after, I mean, if one would go to a particle picture, could one say that after a logarithmic time of generations, you see more or less locally, right, a lot of trees that are filling the space, and they are independent, right, and they produce your Z1 like one golden Watson tree when you rescale it, or produces a Feller diffusion, right?
Yes,
or
yes.
Not one, but
many. Yes,
many.
And actually, yeah. Thank you for the question. It gives me the opportunity to mention that there's a dual result, just as you mentioned, because we also have a duality relationship for BBM to start with. We can essentially carry through all these arguments to the particle system case. And we can say, so if you start many BBMs and look at a scale where you have many particles, but not too many particles, then the average number of particles ends up converging to, to Z1 here. So there's an analog for the particle system, which is exactly as you described.
So if there are no further questions, we thank Lagan and all the speakers of the day.